Chapter number 4 from the book Fundamentals of Physical Geography, NCERT textbook for class 11, chapter 4, Distribution of Oceans and Continents. In the previous chapter, you have studied the interior of the earth. You are already familiar with the world map. You know that continents cover 29% of the earth surface of the earth and the remainder is under oceanic waters. The positions of the continents and ocean bodies as we see them in the map have not been in the same in the past. Moreover, it is now a well accepted fact that oceans and continents will not continue to enjoy their present positions in times to come. If this is so, the question arises, what were their positions in the past? Why and how do they change their positions? Even if it is true that the continents and oceans have changed and are changing their positions, you may wonder as to how scientists know this. How have they determined their earlier positions? You will find the answers to some of these and related questions in this chapter. Continental drift. Observe the shape of coastline of Atlantic Ocean. You will be surprised by the symmetry of coastline on either side of the ocean. No wonder many scientists thought of this similarity and considered the possibility of the two Americas, Europe and Africa, to be once joined together. From the known records of the history of science, it was Abraham Ortelius, a Dutch mapmaker, who first proposed such a possibility as early as 1596. Antonio Pellegrini drew a map showing the three continents together. However, it was Alfred Wegener, a German meteorologist, who put forth a comprehensive argument in the form of continental drift theory in 1912. This was regarding the distribution of oceans and continents. According to Wegener, all the continents formed a single continental mass and mega ocean surrounded the same. The supercontinent was named Pangaea, which meant all earth, and the mega ocean was called Panthalassa, meaning all water. He argued that around 200 million years ago, the supercontinent Pangaea began to split. Pangaea first broke into two large continental masses as Laurasia and Gondwanaland, forming the northern and southern components respectively. Subsequently, Laurasia and Gondwanaland continued to break into various smaller continents that exist today. A variety of evidence was offered in support of the continental drift. Some of these are given below. Evidence in support of the continental drift. The matching of continents, jigsaw fit. The shorelines of Africa and South America facing each other have a remarkable and unmistakable match. It may be noted that a map produced using a computer program to find the best fit of Atlantic margin was presented by Bullard in 1964. It proved to be quite perfect. The match was tried at 1000 fathom line instead of the present shoreline. Rocks of same age across the oceans. The radiometric dating methods developed in recent period have facilitated correlating the rock formation from different continents across the vast ocean. The belt of ancient rocks of 2000 million years from Brazil coast matches with those from Western Africa. The earliest marine deposits along the coastline of South America and Africa are of Jurassic age. This suggests that the oceans did not exist prior to that time. Next point is stalite. It is the sedimentary rock formed out of deposits of glaciers. The Gondwana system of sediments from India is known to have its counterparts in 6 different landmasses of the southern hemisphere. At the base, the system has thick tillite, indicating extensive and prolonged glaciation. Counterparts of this succession are found in Africa, Falkland Island, Madagascar, Antarctica, and Australia. Overall resemblance of Gondwana type sediments clearly demonstrates that these landmasses had remarkably similar histories. The glacial tillite provides unambiguous evidence of the paleoclimates and also of drifting of continents. Placer deposits. The occurrence of rich placer deposits of gold in Ghana coast and the absolute absence of source rock in the region is an amazing fact. The gold bearing veins are in Brazil, and it is obvious that the gold deposits of Ghana are derived from the Brazil plateau when two continents lay side by side. Next point is distribution of fossils. When identical species of plants and animals adapted to living on land or in fresh water are found on either side of the marine barriers. As problem arises regarding accounting for such distribution, the observations that lemurs occur in India, Madagascar, and Africa led some to consider a contiguous landmass, Lemuria, linking these 3 landmasses. Mesosaurus was a small reptile adapted to shallow brackish water. The skeleton of these are found only in 2 localities, the Southern Cape province of South Africa and Iravere formation of Brazil. The 2 localities are presently 4,800 km apart with an ocean in between them. Next point is force for drifting. Wegener suggested that the movement responsible for drifting of the continents was caused by pole fleeing force and tidal force. The polar fleeing force relates to rotation of the earth. You are aware of the fact that the earth is not perfect sphere. It has a bulge at the equator. The bulge is due to rotation of the earth. The second force that was suggested by Wegener, the tidal force, is due to attraction of the moon and the sun that develops tides in oceanic waters. Wegener believed that these forces would become effective when applied over many million years. However, most of scholars considered these forces to be totally inadequate. Next point is post-drift studies. It is interesting to note that for continental drift, most of the evidence was collected from continental areas in the form of distribution of flora and fauna or deposits like tillite. A number of discoveries during the post-World War II period added new information to the geological literature. Particularly, the information collected from the ocean floor mapping provided new dimensions for the study of distribution of oceans and continents. Convectional current theory. Arthur Holmes in 1930s discussed the possibility of convection currents operating in the mantle portion. These currents are generated due to radioactive elements causing thermal differences in the mantle portion. Holmes argued that there exists a system of such currents in the entire mantle portion. This was an attempt to provide an explanation to the issue of force, on the basis of which contemporary scientists discarded the continental drift theory. Next point is mapping of the ocean floor. Detailed research of the ocean configuration revealed that the ocean floor is not just a vast plain, but it is full of relief. Expeditions to map the oceanic floor in the post-World War II period provided a detailed picture of the ocean relief and indicated the existence of submerged mountain ranges as well as deep trenches, mostly located closer to the continent margins. The mid-oceanic ridge were found to be most active in terms of volcanic eruptions. The dating of rocks from oceanic crust revealed that they are much younger than the continental areas. Rocks on either side of crest of oceanic ridges and having equidistant locations from the crest were found to have remarkable similarities both in terms of their constituents and their age. Ocean floor configuration. In this section, we shall note a few things related to ocean floor configuration that help us in understanding of the distribution of continents and oceans. We will be studying the details of ocean floor relief in chapter 13. The ocean floor may be segmented into three major divisions based on depth as well as the forms of relief. These divisions are continental margins, deep sea basins, and mid-oceanic ridges. Continental margins. These form the transition between continental shores and deep sea basins. They include continental shelf, continental slope, continental rise, and deep oceanic trenches. Of this, the deep oceanic trenches are the areas which are of considerable interest in so far as the distribution of oceans and continents is concerned. Next point is abyssal plain. Abyssal plains. These are extensive plains that lie between continental margins and mid-oceanic ridges. The abyssal plain are areas where continental sediments that move beyond the margins get deposited. Next point is mid-oceanic ridges. This forms an interconnected chain of mountain system within the ocean. It is the longest mountain chain on the surface of the earth, though submerged under oceanic waters. It is characterized by a central rift system at the crest, a fractionated plateau, and flank zone all along its length. The Rift Valley system at the crest is the zone of intense volcanic activity. In the previous chapter, you have been introduced to this type of volcanoes and mid-oceanic volcanoes. Distribution of earthquakes and volcanoes. Study the maps showing the distribution of seismic activity and volcanoes given in figure 4.2. You will notice a line of dots in the central part of Atlantic Ocean, almost parallel to the coastline. It further extends into Indian Ocean. It bifurcates a little south of Indian subcontinent with one branch moving into East Africa and other meeting a similar line from Myanmar to New Guinea. You will notice that this line of dot coincides with the mid-oceanic ridges. The shaded belt showing another area of concentration coincides with the alpine Himalayan system and the rim of the Pacific Ocean. In general, the foci of earthquake in the areas of mid-oceanic ridges are at shallow depths, whereas along the alpine Himalayan belt as well as the rim of Pacific, the earthquakes are deep-seated ones. The map of volcanoes also shows a similar pattern. The rim of Pacific is also called rim of fire due to existence of active volcanoes in this area. Concept of seafloor spreading. As mentioned above, the post-drift studies provided considerable information that was not available at the time of Wegener. At the time, Wegener put forth his concept of continental drift, particularly the mapping of ocean floor and paleomagnetic studies of rocks from oceanic regions revealed the following facts. It was realized that all along the mid-oceanic ridges, volcanic eruptions are common and they bring huge amounts of lava to the surface in this area. The rocks equidistant on either sides of crest of mid-oceanic ridges show remarkable similarities in terms of period of formation, chemical compositions and magnetic properties. Rocks closer to the mid-oceanic ridges have normal polarity and are the youngest. The age of rocks increases as one moves away from the crest. The oceanic crust rocks are much younger than the continental rocks. The age of rocks in the oceanic crust is nowhere more than 200 million years old. Some of the continental rock formation are as old as 3,200 million years. The sediments on the ocean floors are unexpectedly very thin. Scientists were expecting, if the ocean floors were as old as continent, to have a complete sequence of sediments for a period of much longer duration. However, nowhere was the sediment column found to be older than 200 million years. The deep trenches have deep-seated earthquake occurrence, while in the mid-oceanic ridges area, quake foci have shallow depths. These facts and detailed analysis of magnetic properties of the rocks on either sides of mid-oceanic ridge led Harry Hess in 1961 to propose his hypothesis known as seafloor spreading. Hess argued that constant eruptions at the crest of oceanic ridges cause the rupture of oceanic crust and the new lava wedges into it, pushing the oceanic crust on either side. The ocean floor thus spread. The younger age of oceanic crust as well as the fact that spreading of one ocean does not cause shrinking of the other made Hess think about the consumption of oceanic crust. He further maintained that the ocean floor that gets pushed due to volcanic eruptions at the crest sinks down at the oceanic trenches and gets consumed. The basic concept of seafloor spreading has been depicted in figure 4.3. Next point is plate tectonics. Since the advent of concept of seafloor spreading, the interest in the problem of distribution of oceans and continents was revived. It was 1967, Mackenzie and Parker and also Morgan independently collected the available ideas and came out with another concept termed plate tectonics. A tectonic plate, also called lithospheric plate, is a massive, irregular shaped slab of solid rock, generally composed of both continental and oceanic lithosphere. Plates move horizontally over the asthenosphere as rigid units. The lithosphere includes the crust and the top mantle, with its thickness range varying between 5 and 100 km in oceanic ports and about 200 km in the continental areas. A plate may be referred to as continental plate or oceanic plate depending on which of the two occupy a larger portion of the plate. Pacific plate is largely an oceanic plate, whereas Eurasian plate may be called a continental plate. The theory of plate tectonics proposes that the Earth's lithosphere is divided into 7 major and some minor plates. Young fold mountain ridges, trenches and faults surrounds these major plates. The major plates are as follows: Antarctica and surrounding oceanic plate, North America with Western Atlantic floor separated from the South America plate along with Caribbean island plate, South America with Western Atlantic floor separated from the North America plate along the Caribbean island plate, Pacific plate, Indo-Australia, New Zealand plate, Africa with the Eastern Atlantic floor plate, Eurasia and the adjacent oceanic plate. Some important minor plates are listed below: Cocos plate between Central America and Pacific plate, Nazca plate between South America and Pacific plate, Arabian plate mostly the Saudi Arabian landmass, Philippine plate between Asiatic and Pacific plate, Caroline plate between the Philippine and Indian, Caroline plate between Philippine and Indian plate north of New Guinea, Fuji plate northeast of Australia. These plates have been constantly moving over the globe throughout the history of the earth. It is not the continent that moves as believed by Wegener. Continents are part of plate and what moves is the plate. Moreover, it may be noted that all the plates without exception have moved in the geological past and shall continue to move in the future as well. Wegener has thought of all continents to have initially existed as a supercontinent in the form of Pangaea. However, later discoveries reveal that the continental landmasses resting on the plates have been wandering all through the geological period, and Pangaea was a result of converging of different continental landmasses that were parts of one or the other plates. Scientists using the paleomagnetic data have determined the positions held by each of the present continental landmass in different geological periods. Position of the Indian subcontinent, mostly peninsular India, is traced with the help of rocks analyzed from the Nagpur area. There are 3 types of plate boundaries. First is divergent boundaries, where new crust is generated as the plates pull away from each other. The sides where plates move away from each other called spreading sides. The best known example of divergent boundaries is mid-Atlantic ridge. At these, the American plates are separated from Eurasian and African plates. Convergent boundaries, where the crust is destroyed as one plate dived under another. The location where sinking of plate occurs is called subduction zone. There are 3 ways in which convergence can occur. These are between oceanic and continental plate, between 2 oceanic plates, and between 2 continental plates. transform boundaries where the crust is neither produced nor destroyed as the plate slide horizontally past each other. Transform faults are the planes of separation generally perpendicular to the mid-oceanic ridges. As the eruptions do not take all along the entire crest at the same time, there is a differential movement of a portion of the plate away from the axis of the earth. Also, the rotation of the earth has its effect on the separated blocks of the plate portions. Rate of plate movement. The strips of normal and reverse magnetic field that parallel the mid-oceanic ridges help scientists determine the rate of plate movement. These rates vary considerably. The Arctic ridge has the slowest rate, less than 2.5 cm per year, and the East Pacific rise near Easter Island in the South Pacific about 3,400 km west of Chile has the fastest rate, more than 15 cm per year. Force for the plate movement. At the time what Wegener proposed his theory of continental drift, most scientists believed that the earth was a solid, motionless body. However, the concept of seafloor spreading and the unified theory of plate tectonics have emphasized that both the surface of earth and the interior are not static and motionless, but they are dynamic. The fact that the plates move is now a well accepted fact. The mobile rock beneath the rigid plates is believed to moving in a circular manner. The heated material rises to the surface, spreads and begins to cool, and then sinks back into deeper depths. This cycle is repeated over and over to generate what scientists call a convection cell or a convective flow. Heat within the earth comes from two main sources, radioactive decay and residual heat. Arthur Holmes first considered this idea in 1930s, which later influenced Harry Hayes' thinking about the seafloor spreading. The slow movement of hot, softened mantle that lies below the rigid plate is driving force behind the plate movement. Next point is movement of Indian plate. The Indian plate includes peninsular India and the Australian continental portions. The subduction zone along the Himalayas formed the northern plate boundary in the form of continent-continent convergence. In the east, it extends through Rakhinioma mountains of Myanmar towards the island arc along the Java Trench. The eastern margin is a spreading site lying to the east of Australia in the form of oceanic ridge in southwest Pacific. The western margin follows the Kirthar mountain of Pakistan. It further extends along the Makrana coast and joins the spreading site from this Red Sea Rift southeastward along the Chagos archipelago. The boundary between India and Antarctic plate is also marked by oceanic ridge, divergent boundary, running roughly west-east direction and merging into the spreading site a little south of New Zealand. India was a large island situated off the Australian coast in a vast ocean. The Tethys Sea separated it from Asian continent till about 2 to 5 million years ago. India is supposed to have started her northward journey about 200 million years ago at the time when Pangaea broke. India collided with Asia about 40 to 50 million years ago, causing rapid uplift of Himalayas. The position of India since about 71 million years till the present are shown in figure 4.6. It also shows the position of Indian subcontinent and Eurasian plate. About 140 million years before the present, the subcontinent was located at the south as 50 degrees south latitude. The two major plates were separated by Tethys Sea, and the Tibetan block was closer to Asiatic landmass. During the movement of Indian plate towards the Eurasian plate, a major event that occurred was the outpouring of lava and formation of Deccan Trap. This started somewhere around 60 million years ago and continued for a long period of time. Note that the subcontinent was still close to the equator from 40 million years ago, and thereafter the event of formation of Himalayas took place. Scientists believe that the process is still continuing and height of Himalayas is rising even to this date. Thanks for listening. This is for today. Thank you.